layout and the fabrication. يعني if we see a simple layout, how to handle it, or something that we have already seen, what are the different layers if you see a cross section, or if you see something that you have seen before, and then how to build the Euler path, and how we interpret the nodes and stuff like that. Okay, so I will be sending you some instructions between today and tomorrow, but I just wanted to give you some heads up. Okay, طيب هلا last time we were studying the Euler path, and we said that in order to build the layout compactly, we would like to build the PMOS transistors and the NMOS transistors to be as intact as possible. Yeah, let us look again at this circuit here. And if we have this circuit here, and we don't want to build the layout very intact, if we just want to do it the basic way, what we might have done is that we might have said, well, I have two PMOS transistors, so I am going to, for these two PMOS transistors, just simply draw A, and I'm not going to put colors here, but for the simplicity. So this is the PMOS transistor for A, and this is the PMOS transistor for B. And I have another PMOS transistor. Now, it is definitely better for me to align them, so at least I will put them under each other here because they are simple. They are two transistors for N, and this is another PMOS NMOS transistor for B. So I have A and B. And then I would have started to connect them together. So I would have said, well, these two gates are the same, so I can connect their poly really, and those two gates are the same. I can connect their poly, same material. And then A, well, one node from A is VDD. Okay, and then one node from B is VDD. I could have connected this way, and then this is the common node. So this is the common node between the two. And then in the pull down network, so هاي بنكون خلصنا البول up. Then we look at the pull down network. Then we can say, well, B is connected to ground, so I can connect B to ground. And then I have the common node 1 here, so I assume that this is node 1 and I connect it. And then the output is at Y, so this is the output node Y, so I need to really connect it to this common node, which is the output as well. Okay, so what is the difference between this and the common stretch? What did we really do when we drew the Euler path? We tried to make 1P diffusion, يعني eliminate this separation, هاي separation اللي هون between the two transistors which are connected and are of the same diffusion type. We tried to find a path that will visit the transistors, each one only once, in the same order, for the purposes of two objectives. The first objective, maintain the order, يعني have the same input stretch from N to P. اوكي، يعني مثل هون ال A طلعت من ال A لل A، ال B من ال B لل B، ما في كتير not much routing and to switching things around. And the second thing, the objective of the Euler path is to really have a joint diffusion where possible. يعني this makes the area of the cell smaller. لأنه if I want to treat each transistor alone, it's going to take more area. But if I know that this is a common node and it's of the same type of diffusion, I can simply join the two transistors together. يعني هيدي صارت, I have now, the way we draw it now, I have A and B, and this area is common and it's diffusion. I didn't have to go up to the metal, draw a wire and go down, and this saves a lot of area. The design will be more compact. And the same in this region here. Okay, so from this perspective, this What does this do? This also helps me save in the area, and it will introduce area savings. So advantages, I will be saving area, and indirectly what? Capacitance. Okay, I will be saving area and capacitance. ليش؟ لأنه when this was two diffusions, it was two regions, so it has double the capacitance later when we study things than if this is only one region and I don't have to go up to the metal and come back down, so the parasitic capacitance will be less. Practically, if we count this as two capacitors, this will be one. يعني إذا بدنا, if we want to count it that way. And of course, here we're assuming that all the transistors are of the same width for our purposes. Okay? Clear what the Euler path helps us? It helps me find a stretch of P diffusion and a corresponding stretch of N diffusion that will guarantee that the input is going to go all the way from N to P in the same order. Okay, so it goes in the same order, and that guarantees that I have as much joint diffusion area, يعني nodes that are common are really connected with diffusion as opposed to going up to the higher layers and back down. Okay, هذا الobjective لليولر. Yes.
What do you exactly mean by stretch?
Okay, so stretch يعني, let me هلا redraw it here. So I'm going to draw it on the next slide. One second. So if you look now, what we are differentiating is we are differentiating between drawing in the PMOS and alternative one. Okay, I draw transistor A, I draw transistor B. Okay, and I draw a connection, pardon me, I draw a connection between them, right? So I draw a connection between them, right? So فعليا what we have here is we had the diffusion for the NMOS. Let us assume that these were the NMOSs, and the diffusion for the second NMOS. They are separate, right? And then I have to build contacts and go up and connect them with the metal. An equivalent circuit in the N would also have been what? For me to draw A, right? And B are these two transistors. What is the topology of those two transistors? If I want to draw the lower ones, what is this? If I call this node 1, 2, 3, transistor A between node 1 and 2, right? And transistor B is between node 2 and 3, right? Is that correct? How did I join node 2 in this phenomenon? How do I know that 2 is connected, that they are connected at node 2?
Using the same diffusion.
Using the same material, sharing the same material, right? Whereas in this circuit, it is the same. So I have transistor A. Okay, so this is node 1, 2, 2 prime, and 3. So A is between 1 and 2, and B is between 2 prime and 3, and I connected them, pardon me, I connected them using the metal here. حطيت contact لوصلهم صح؟ So these two are the same, but this will take more area لأنه I separated the transistors, whereas I could have benefited from lumping them together. Okay, because I could find a path that can walk through this. Okay? طيب, great. So
okay.
This is
could you please, I'm sorry, contrast it with the second advantage? And I thought there was a difference between a stretch and a joint diffusion because you mentioned them as separate points. Okay,
so the joint diffusion, okay, based on the design rules, it can have a minimum area, صح? And since it has a minimum area, it occupies naturally specific capacitance. Okay, يعني إذا أنا بدي أعتبر هيدا عم يخلق لي capacitor, if you remember in 311 we used to call this CDB for example. Okay, وهيدا عنده another capacitance here. Let me just erase this. If we look at this here, in real life, each one of these will have some capacitor to ground. So we can call this CDBA, and this will have another capacitor to ground. Any entity, any square on the circuit will have a capacitor. Later we'll learn about it. Very, very basic. And then this will be CSB for transistor B, right? And هيدي source تاعت B. So I will have, in this scenario, this will have its own area allocated for it to exist, to be a transistor. And this will have its own area allocated to it to be a transistor. يعني these will have one capacitor, two capacitors, right? So if this is C and this is C, this will be C and C in parallel. The effective will be 2C, right? Whereas in this scenario here, when I join them together, what is it? Is this shared or not?
Shared, yes.
It is shared. So I will have one capacitor whose value is C. So بلش يبين معنا الفرق إنه الاريا صغرت لأنه first I have to draw this and make a separation between them حسب the design rules. And also the capacitance, which was counted twice because I'm treating each transistor individually, when I joined them or glued them together at this common diffusion, which is anyway has to be glued through a metal because they are connected. When I glued them using diffusion, I also reduced the capacitance which I am handling. يعني node 2 here appears once, whereas node 2 here is appearing as 2 and 2 prime, it's appearing twice. صح؟ يعني هي فعليا هذه كلها one node موصولة بمثل. So node 2 appears twice. Is this clear?
Yes, Professor, thank you very much.
Okay, thank you. So,
Professor, can I
yes.
ask also a question?
Yes, please.
So instead of doing directly the Euler path and connecting them through a diffusion, can we do it the method that we did at the beginning of this lecture and then replace these metal connections with the diffusion?
هلا, what will you see is that later, as the transistors become more, then you will need to find if a Euler path exists, and you need to find the common Euler path. لأنه أنا هون I knew that I have to go through AB and connect them, but later I will not know really what order unless I visit them through that specific order. يعني هو Euler path is nothing but determining, if you want to know what's the definition of the Euler path, is determining the specific order of inputs that is common to N and P. And then really, if you want to draw them independent and then push them to join them, it's going to be almost the same as just drawing them and ordering the A and B and C, as we will see as we practice. Okay, so who are just guessing if I have to put A, B or what, لما يصير more than 2, you will see why we need the Euler path.
Yes.
Okay, طيب, thank you. So now, if we look at the stick diagram, we said last time that we took the pull up alone and we took the pull down alone, and we identified a path with some starting point that visits each transistor once. And this path, if it bears the same name, يعني BA, then it will allow me to simply draw a P stretch diffusion and an N diffusion stretch, and then I will follow the node labeling to connect the different nodes. يعني first B goes to ground, okay, then there's a common node between A and B. I don't do anything, it is connected, then I have the output. And then in the P stretch, I'm starting from here. So B is connected to VDD. I visit B, I have the output node which is common between A and B. I don't need to join them. And then I visit the transistor A and I end at VDD. A has to be connected from the other side to VDD. Then I need to join the output because it exists between the P and the N network. Okay, so this is the stick diagram. Okay, hello. If we ask you what is the capacitance at the output node, so what is C at node out? If we tell you that one diffusion for N or P has a capacitance C, then how many diffusions is out connected to? Can we count them? One in the PMOS and one in the NMOS, so it is 2, right? Assuming same widths، يعني هيدا عم نعتبر same width all devices. إذا قلنا لكم كل slot in the diffusion هي 1C، okay? Every slot is 1C، الأوت موصول مرة بالP ومرة بالN. وطبعا إذا غيرناها إذا كان CP غير CN حتكون 1CP and 1CN in this example. Okay? طيب هلا this explains briefly. Let us look at this example. Now he's giving me y equal A or B into C. Thank you, Joe, for answering. So now I have y equal A or B into C bar. And first I need to draw the circuit, right? So I'm going to draw the pull-down network. And the pull-down network is going to look like this. I have y bar equals A or B into C. So I will have A or B. Okay. And with what? With C. This is my pull down, highly ground. Okay, and this is my out. Hello. The pull up network, it is going to be the complementary. So اللي كانوا parallel حيصيروا series واللي هن series. So بلش بالinnermost. So for the pull up network يعني هاي هي A parallel ل B into C. بالpull up حتصير A series ل B parallel ل C. وبلش بالinnermost. يعني I will have A series مع B and all of these are parallel to C, and this is connected by VDD and out. So this is my circuit. Okay, this is my circuit. Now I want to draw the stick diagram for it. I need to find the Euler path. I want to find a common Euler path. Okay, so let us start with the pull up لأنه loop is clear here. Pardon me. The loop is clear. So let us start with the pull up network. So if I start from here or from here, it doesn't matter. We can start from VDD. Typically, it is always good to pass through out once. يعني نخلي الأوت هي تكون transition حتى يبين عنا less capacitance. So I can visit C, then B, then A. Okay, so this is CBA in this order. And in the pull down, can I visit CBA? I can start from here, CBA. I can stop at any node and start at any node, or I can stop at the same node that I started with. What matters is that I visit every transistor only how many times? Once. يعني ما فيني أمرق على الترانزستور multiple times. And we'll take examples where it is not possible to do this, so we break the Euler path. Okay? But is this clear how we passed CBA? So we will draw the N diffusion, and we will draw the P well and the P diffusion, and we will have the VDD and the ground. Okay, and we will have now, since they are of the same order CBA, I can now put poly 3 stretches for the 3 inputs, and they will be called C, B, and A, and it is the same input up and down. Okay? طيب هلا let us see what are the intermediate nodes so that we call them. This is a ground. This is an intermediate node 1. This is out. This is VDD. So this is an intermediate node 2. Okay, so let us start. Follow the arrow. Yeah, follow the arrow. Following the arrow, we start from 1. So 1 is C, the source of C connected to ground. Sorry, pardon me. Sorry, C is connected to ground. Pardon, صرت حتى أنا غلط أنا أشرح لكم. So we start from here. C is connected to ground. We visit C. We go through what node? 1.
B source.
صح, the source of B, which is practically node 1 اللي هي common بين C و B. نطلع لوين على أي نود بعد ما نقطع ال B؟ على out. We go through A and then we come back to what node? We stop at 1, right? Stop at node 1. طب خلصت ال N. Okay, هلأ نرجع على B. We are starting here. We are starting from VDD. We go through transistor C to node out, which is a common drain بين ال B وال C. نقطع على ال B. Okay, نوصل على node 2 اللي هي بين A و B. And then we visit A and we go back to what node? VDD. Okay? هلا, where do the input and output, where do the N and P networks connect? They connect at node out. So I need to do this connection. Are there any nodes that are not connected in this circuit? هات لنشوف. في عندي 1. So node 1 needs a metal connection. ليش؟ لأن the diffusion is in 2 places. So انحكمت فيها هي. Okay. So هي shared بين B و A و C. بس هون it is the shared part بين B و C. I need to connect A to them. So I have to make 2 metal connections. إذا قلنا ال P diffusion عنده CP وال N diffusion block يعني every square عنده CN. What is the capacitance at the output node?
مش CP plus CN.
Exactly, it's CP plus CN. طيب والcapacitance at node 1? كم diffusion وصلنا؟
2CN.
2CN, exactly. Okay, so we connected to CNs. I'm not drawing it to scale, so هي مبينة أكبر من هاي, بس هون each sketch هو عبارة عن diffusion عنده CN هون. Okay, so if it appears twice in the N diffusion يعني عندها 2CN. It appears once in N and once in P يعني عندها CN plus CP. Okay.
But for node 1, we connected with a metal, so بطل diffusion.
إيه عم نعتبر إنه الميتال is too short over the gate. يعني أنا عندي 2 regions لما بنرسم stretch للسيركت. إذا اعتبرنا هاي هون وهاي هون وهاي هون. عندي هيدي عندها capacitance لجراوند وهيدا سكوير عنده capacitance لجراوند وأنا وصلتهم ببعضهم. ما هو الجرين بعده موجود. I cannot remove it. The transistor has to exist, right? So each stretch هي عندها وصلناها بمثل بس مش هي. هيدي اسمها هيدا الديفيوجن اسمه نود 1 وهيدا الديفيوجن اسمه نود 1. Okay, يعني if I want to draw it for you 1 second, I will just make a little 3D sketch for you لحتى هيك تصير أوضح. If we want to look at node 1 حيكون أنا عندي a big عندي 3 hot transistors. عندنا البولي وبولي صح وبولي لل A. Okay, and in here really what do I have? I have the transistors drawn. Okay, sorry معلش مش كتير منيحة الرسمة. Okay, so I have the transistors drawn. So هون البولي للC لنفترض، هون البولي للB، وهذا البولي للA, right? And then the transistors are drawn such that I have a common diffusion. كيف جاي الديفيوجن هلا؟ عندي diffusion هون، معلي هاي not to scale مبينة كبيرة، عندي diffusion هون، عندي diffusion هون، وعندي diffusion هون، وهو كلهم هني n plus. Okay, so هيدي n plus، هيدي n plus، هيدي n plus، وهيدي n plus. Okay, and this material here now represents كل وحدة منهم عم تمثل لي transistor. And then what we did is we said, well, I'm going to create a contact that will go up from here and connect this node here. صح? Okay, so then this is the diffusion still exists. يعني هاي عندي diffusion هون source drain material, right? So let us assume now that C is equal to 1 and B is equal to 1. Let us assume that C is on يعني B is on. What is going to happen? The channel will turn on and the channel will turn on. And if this node is the output node, then I will connect ground لوين؟ للout. صح? Okay. So now let me assume that all of them are on. ساعتها بتكون ال A كمان واصلة معه. بس is it clear how node 1 is really built? So node 1 now is nothing but the common diffusion. يعني أنا كان عندي 2 ترانزستورز لما كنا نرسم الترانزستور هيك، إذا كنا نرسم السي لما كنا نرسمه ككروس سكشن مش كنا نعمل له n بلس ب n بلس وتجي السي فوقه، هيدي السي. ونفس الشيء if I have B here and B used to have n plus and n plus وهيدي ال B فوقها. Okay, and I have also A and A would have the different diffusions that are out there n plus و n plus. هلا نحن كيف سمينا النودز لما لحقناهم؟ هيدي كانت ground صح؟ هيدي كانت الكومن نود 1 وجمعناهم مع بعضهم as one stretch of diffusion. هلا نمحيهم ونوصلهم، وهيدي وصلناها هون على الاوت، وهيدي هي نود 1. so طلعنا من نود 1 لهون وصلنا بكونتاكت. Okay, now how do we have them in this example is as follows. بدل ما يكون هيدا بعيد عنه اجا البي كفى بنفس الديفيوجن. so اجا البي قعد هون كفى هيك وعملنا له diffusion لإله separate. so هيدا البي اجا هون. Okay, and this is the diffusion around B. And then we continued with the substrate and we really drew A here. And then we drew the diffusion around A. This is what we mean by the stick diagram, right? Okay, شو صار عنا؟ صار عنا common diffusions هلا، صح؟ يعني إذا نلحقهم بالليبلينج اللي مشينا فيه باليولر باث. This is node 1, this is common node out, and this is node 1. And what we did, we connected them through a contact. So how many diffusions are there for node 1 now? 2, right?
Yeah.
Okay, so practically نحن عم نجي نرسمها هيك إنه هيدي stretch وعم نجيب A C عفوا B and A. okay, لنشرح إنه هيدا اللي هو هون common بين C and B هو فعليا هيدا ال common one، وهيدا اللي هو هون بين B and A للأوت وهيدا ال common and so on and so forth. ولما يدور الترانزستور بيخلق لي channel أو ما بيخلق. Okay, so literally anytime I see this repeat once or twice I'm going to say that it has 2 diffusion capacitance or so on and so forth. حدا عنده سؤال? Anybody has a question or is it clear?
Professor, at some point in the previous slide, you drew a small X بعد diffusion, بس هي بدش contact صح؟ بالسلايد اللي before this.
إيه معلش sorry that في عندي أوسع. Let me close.
I'm not sure which one. It's
this one. It moved
the
back.
stick diagram without doing the squares.
إيه
this one.
هيدا.
إيه يعني مثلا على node 1 في X.
Okay.
This is not a contact صح؟
هلا هاي عم اقول لك انا انه هون اذا كانوا بعاد اذا مرسومين individual transistors I have to make a contact to connect them. يعني
yes but you know same diffusion.
لما يكونوا same diffusion مثل هاي ما بدك ترسم X. لا ترسم X لما بتطلع من one diffusion to another. يعني I think I don't know if I erased it by mistake or it is still there. لما رسمناه stretch the 3 of them. Okay, maybe I erased it by mistake. I'm sorry. When we drew the stretch for the 3 of them. Okay, مثل هون. لا عفوا مثل هون like here. I have to draw the X. Okay. I have to draw the X لأنه من وحدة لوحدة رايحة بدي أوصل two diffusions ببعضهم. بس if the intersection means that they are connected ما بده contact. هون رسمت الإكس لأنه عم بوصل الأوت على الأوت.
يعني مثلا عدتو بديش
عدتو ما بدنا هيدي بس أنا عم بلحق النوتس مش رايحة المطرح يعني contact will not take it anyway. Okay, anybody has any other questions?
Thank you.
Thank you. طيب لكن هلا let me save this. I will post it online for you and let us go back and open the more about complex gates. Okay, so here we're going to take examples and we're going to explain what Euler path means in geometry. So إذا رحنا فتشنا بالويكيبيديا, if you search for Wikipedia about Euler path, it says it's a path in a graph which visits every edge exactly once, and it will give me this graph, and it will ask me to find the Euler path. And sometimes we can find more than one Euler path, and sometimes we cannot find a Euler path. So here, if I start, and let me see if I can draw with a different color. If I start here. Okay, I can go like this. I can visit this edge. I can visit a node more than once, but what matters is that I don't visit the edge twice. Or I can start here. I'm visiting the node, coming back to the node, but the edge is being visited. هلا هيدا مثلا بدي اطلع فيه لهون ما فيني وقفت. شو صار فيه هيدا لما بلشته هيك؟
نفس الإدج.
اضطر امرق هون هيدي ما بتزبط. Okay, so this is how we reject a Euler path, or this is how we accept a Euler path. Okay, so فإذا in this scenario I started from here. Okay, I visited this path, I went back, went up and come back, and this way I visited every edge once. So the most important thing is to be able to visit every edge only once. هلا اوكي سوري froze. سوري هيدا لأبن الايباد. I apologize. Okay, so هون let's keep the annotations and let us come back here from the slide. So لكن our goal when we are building complex gates is to represent each network NMOS or PMOS by a graph where the transistor is an edge and the node is a vertex, يعني مثل VDD, ground, out, والinternal nodes. And we want to find a common Euler path for the two networks. ليش؟ لأنه دغري هيدا بيعطيني regular compactness. All our layouts have VDD going in this direction. All our layouts have the inputs going in this direction. And the output can thus be connected to the next gate in this direction. Okay, so هيدي regularity بتساعدني لأعملها compact. In addition to this, the NMOS diffusion is one stretch. صار عندي minimum area للtransistors. This helps to reduce the diffusion capacitance اللي نحن حكينا عنها already اليوم. Okay. And this is an example where we talked about the circuit اللي هي كانت NAND gate. Okay, this is an example of the NAND gate where A and B share the output node بالpull up. Okay. وأخذنا الباث اللي هو كان like this for the pull up and the stretched path for the pull down network. Okay, so this is the example of the NAND gate. طيب great. هلا خدنا الإكزامبل هيدي رسمناها خلاص ما بقى في داعي we don't have to go over it again. Now here he is showing you though this gate in two possible ways. One possible way he what we drew where this is the N. Okay, sorry, where this was the N, okay, and this was the P, and we drew them uninterrupted. يعني عملنا ال N لحالة وال P لحالة وصلنا هو قلبهم وصلنا node 1 هيك ومشينا and we worked things out. And another example where he took the input ACB. Let us see if we pick ACB what happens. And let me go back to this and draw the gate which was drawn A or B, okay, in series with C in the pull down, and we drew in the pull up network A series with B, and they are all in parallel with C. And he's saying, well, what if I pick the path to be ACB? يعني حيطلع من هون يروح على C ويجي عند ال B. Okay, and let us see what happens if I do it this way. AC. Now can I visit B again? To visit B I have to go through C twice, I cannot. So this means that I have to treat B as an independent stretch. صح؟ يعني in the pull up, even if I draw A, let us draw the poly first. Okay, so let me clear that. So ACB, it's of the order A, C, and then B. Okay, so بالpull up كان عندنا equal stretch ماشي حالة one stretch, but in the pull down what do I have? In the pull down I have AC and then I have B alone. Let's see why. Let me draw VDD and let me draw ground and let me label the intermediate nodes. This is 1, this is out, VDD and the ground, we know them, this is node 2. And let us follow the node connections just like we see here. So the first thing here is ground. So let me see, I started this way, I went down, so I started from out. Okay, so in the path we started from out. So the first node here is out. And then we visited C at node 1. So جينا على الcommon node اللي هي 1. And then we visited C and we arrived to ground. So هاي نزلت على ground. Okay, and then now I can start B wherever I want. I visit B up or down. So I can make this, doesn't matter, out. And I can make this node 1. Okay, do you see now why I cannot continue the same stretch in B and C? بينما بالupper one I started from node 2, so this was 2. I continued to VDD, so this goes to VDD. هيها هون صرنا على VDD. I passed through C, and after C I reached node out. And after B قطعت B وصلت رجعت على node number 2. So I could do the whole path and I can connect these together. And out I need to connect it also and node 1. But what does this tell me? What is the capacitance at node out? شو الكاباسيتنس عن node out؟ إذا اعتبرنا هيدا عنده CN وهيدا عنده CP.
2CN plus CP.
Exactly, 2CN plus CP. Okay, so and also I have two diffusions and I need the spacing between them لأن مش عاملتهم ملزوقين ببعضهم, they are different nodes. So this means that I'm going to lose on area. يعني حتى هيدا ال P is really distorted. It is not very compact if you want to draw a regular layout. Okay, so you see the difference when we pick the wrong Euler path, what happens? يعني I cannot push this onto this لأنه هدول different nodes. Okay, طب great. So this slide is telling us what happens if we have a interrupted diffusion. على هون هو يمكن رسم ال interruption, أي لا مبين احنا حاطه بال B. And you can see this is one stretch and this is another stretch. Okay. طب هلا let us take more examples on the Euler path. So here he is now okay, sorry. Okay, so now they're telling us what the objective is to make an unbroken row of devices, okay, to minimize the diffusion breaks, to minimize the separation by the diffusion. The gate connections are aligned, يعني كل البولي نازل بنفس الاسم, the same place, linear, ما في difference. The layout will have a single diffusion strip. كمان بالPMOS it's more important لأنه عنا annual والاريا بتصير أكبر, bigger and bigger. And we need to have the inputs ordered according to a common Euler path. So هلا نحن ما حنعمل construction لجراف, هون عم يشرح لنا how you construct the graph from the transistors where they are the edges and the nodes are vertices, because we know how to navigate on the circuit itself. But he's saying انه make a pull down network, يعني pull down graph, and make a pull up network, يعني أنا عندي pull down network وعندي pull up network وبدي طلع common Euler path. هيدا أهم شيء, that's the most important takeaway from this example. Okay. طيب هلا عم بقلنا if we have now an OR and invert gate مثل not C into A or B, which is what we just took. Okay, so this is the logic circuit and this is really how we draw it, and he's showing you how you make the graphs, but we don't need that because we can easily see that this is an edge and that this is another edge and this is an. Okay, so if you can navigate here, you don't have to go in this direction. And then he's showing the complementary of it for the PMOS. We don't need to worry about it. Okay, don't worry about it. So هلا هون عم يشرح كمان انه كيف we find the path. Don't worry about those two slides. Let's look at another example, which is, what is this equation? It is A or B into C or D or part. Okay, so this is the equation for A or B into C or D or part. So let us see how we handle this circuit and how we draw its Euler path. Okay, the difficulty is going, the PMOS pull-up network is easy. I can go CDBA. Let me see if I follow this order, CDBA, if I can find a path. So I cannot start from here لأنه أكيد ما حأرجع أنزل على B وال A. So I need to start the CDBA different. So I need to start with the CDBA this way. CDBA. Okay. Great. So I found a path that visits each transistor only once, CDBA, and let me name the nodes. هيدي ground بنعرفها. This is out. We know it. Okay. The intermediate node is this common node which has 4 transistors. Okay, and typically if it were flat, what would be if I was drawing each one of the transistors alone, but بوصل node 1, how many CN diffusions would I have had at node 1? كم ترانزستور موصول فيها؟ 1 2 3 4. So كان طلع عندها 4 لو كان يعني discrete transistor, right؟ لأنه لو عندي discrete transistor هيدا A B C D كان قلنا A بين ground و 1. We said B is also between ground and 1, and C is between out and 1, right? And D is between 1 and out. How many diffusions لنود 1? 4. So عندها 4 CN لو كنا عم ناخد distributed أو discrete transistors. Okay. Now, if I want to look at this circuit, if I want to look at the same circuit, but I want to have it, and let me delete this, I don't want it. If I want to have this circuit now and draw the Euler path for it, okay, I am not going to have them discrete. I will have them, of course, يعني one stretch. So here we said it is CDBA, and it's going this way, and here we'll have CDBA, and this is the common node 1 out. Here I have node 2, node 3, which are internal nodes, and this is CDBA. So if I want to draw this, I will draw the N diffusion, I will draw the P diffusion, and I will draw the VDDs and the ground. So this is always VDD, this is always ground. And here I will have 4 red stretches which will represent the CDBA in order. هيدي CDBA in order. هلا we start to connect the nodes. I'm starting from node 1. هلا notice here, because I start and end with it, I'm going to have 2 diffusions. Okay, so here I'm starting from node 1 in the NMOS. لا عفوا, sorry, هي على الهبل. I'm starting from node 1 in the NMOS. So this is node 1. And then I go to out. And it is a common node between D and C. Then the path goes to, after D, it goes to node 1 again, which is common between B and D, and then it goes to ground. And then after that, I visit A and go back to node 1. Okay, so maybe this is not the most efficient implementation, okay, because I have repeated 1 3 times. So I have 3 diffusion capacitance, and these need to be connected, right? هيدي بدها تتوصل بهاي, بدها تتوصل بهاي. Okay. So هلا بالpull up network, where did we start? We started at VDD. Okay, so this goes to VDD. I visited C, I went through node 3. Then I visited D, then I went to node out. And then I visited B, I went up through node 2 here between A and B, and then I went back to VDD. Okay, so this is easy, no nodes need to be connected. Then I have to connect out, هنحطه بغير color, from here to here, of course. Okay. Okay, so in this scenario, we have the capacitance for the out of 1 CN plus 1 CP, and the capacitance for node 1 who is 3 CN. All other intermediate nodes have only 1 capacitance. But could I have found a different path that may have reduced the capacitance at node 1? هيك لنشوف.
Symmetric one
that does not start at node 1, and مجرد ما بلشت وخلصت عليها, it will appear twice at least, right? So exact. So هشام عم بيقول BDCA. Yes, that's a possible solution. And let's take this بس هيك out of fun and show you how we would handle it, and then we continue with the rest of the slide. أو هيدي حنلحق هاي بعد. Yeah. So okay. So now if I want to take another path, and let me see what it could be. So here, if I take BDCA, من هون حيكون حبلش هون BDCA. كم مرة I visited node 1 بالpath?
2 times.
2 times. So most probably I will have 2 diffusions, right? And if I want to do the same, I will have to start from here BDCA. So هون حكون مرقت على كل الnodes once إلا node 2, and I can draw the equivalent circuit for it. Okay, so I could have chosen this path, and I can start to guess now how I find things. Okay, طيب great. I will send some emails to you over between today and tomorrow, and you can practice on testing this path with DCA. and I will post the previous set of slides and those notes up to here on Moodle as well. Okay, thank you everybody. حدا عنده سؤال؟
Yes.
Mm.
So, okay, in the previous way, the way we did the pass, we visited node 1 3 times. So we had 3 diffusion for C1, 3 CN. But in the new way, BDCA, we got in the pull down, we passed through node 1 twice. So we got 2 diffusions and we had another diffusion in the pull up. So in total, we had 3 diffusions.
مش لوان مش لوان.
لا 2.
ايه 2 زادت الأي خفت شوي.
Yeah.
يعني but what you
is
lose in one place, what you lose in one place, you will gain in another. You will get penalty for it in another. But maybe بدل ما تكون ال1 كتير choked خففنا عنها شوي. So هون بتصير simulation analysis and do I want to balance things more or do I want to stress on one node more, right?
Yes, okay.
Typically, if we start with VDD and end with VDD or start